So welcome again to the Software Project and Process Management lecture. I'm Jens Heidrich, and I'm happy that you join again for another module of the lecture, which is about software quality models. And so in the past, we learned how we can set up measurement programs, what data we potentially might collect, for instance, from a static code analysis and other mechanisms. And in this lecture, we will try to get a little bit more insights into what is the quality of a software. So how is it defined? What aspects are important? Because in practice, it's very difficult to say, okay, our software should have a very high quality. What does this mean? Does it mean, okay, it should be reliable, there should be no defects in the software? That's an important property, don't get me wrong. But there are a lot of other properties that you might think of. So for instance, in our days, a lot of software components have a very long life. Yeah? So they're used over decades. So it's also important to be able to maintain them over time. And maintainability for that reason is an important aspect. Also, you might have special interests in different other properties of your software, like the performance of the software or the security of the software, so that data cannot get lost or unauthorized people might be able to access your data. Or in terms of embedded software, functional safety is also a very important property. So there are different so-called quality aspects that might be of importance. And so we had a lot of research projects on the topic of software quality modeling. And so let's have a look onto the typical approach that you follow there and how you can build up these models in practice.
Learning goals for this module are as follows. First of all, we will have a closer look to what quality models are good for in general, what quality models are, how they are defined, how they are specified. Then we will have a look to some international standards in this area. And we will also have a look to a process for systematically constructing your own quality models. And we will finally also check what are typical application fields of quality models. In the last learning module about static code analysis, we already had an initial look to some aspects regarding software quality. On the one hand side, we were mainly focusing on source code as our object under analysis. And we had several quality aspects that we took a deeper look on. On the one hand side, code smells, so things that can make adapting a software quite difficult. So maintainability was the quality aspect related to that. And on the other hand side, potential bugs or issues that were identified following some rule checkers on the source code, so places in the code that may potentially lead to some failure of the software-based system while using the system. So this was mainly related to the reliability of the system. But as we will see in this module, there are many more quality aspects to be considered. And it's not only about the source code, it's also about other artifacts of your software development process. And software quality becomes a quite important success factor in our days. Increasingly, the selling points of many products become software. So in that way, in that sense, also the quality of the software becomes more and more important and can be really a critical factor in the market. So if you have a quite good software quality, or for your customers, software quality is on the one hand side, if you invest in software quality, of course, you have to put some effort and money into getting good quality. And you need to balance that, of course, with how important software quality is for your customers. But if you produce software of very bad quality, your customers may start complaining, and it will hinder adoption of your software in the market. And if you have an acceptable or very good software quality, then customers will probably like your product and start using it more frequently or more intensely. And the problem with software quality is that once it's spoiled, it's very hard and expensive also to fix it. So once you have probably detected, if you start bothering about software quality too late, then maybe it's already too costly to fix it. And that's also the experience that we got from many, many years of working in that field. When we talked to companies, please analyze our software, whether we have some issues in there or what can be improved regarding that piece of software, that it turned out that sometimes the effort in just taking the functionality or the specification and do it from scratch was easier and less effort consuming than correcting all the issues that we found there. And well, a popular example, not from the area of software development, but from the construction area, is the Tacoma Narrows Bridge that collapsed because even moderate winds produced an aeroelastic flutter. So the bridge was starting fluttering, and finally it collapsed. And so this was not investigated or was not found in the initial design. So the bridge was really constructed and start being opened for the public when in that specific area where the bridge was raised, the environmental constraints were in that way that the bridge started with that fluttering effect and finally collapsed. So that was, of course, a huge disaster. And that also, I think, quite nicely illustrates that software quality analysis does not start with the source code. So source code, it's fairly easy to analyze because it's a formal piece of artifact that we get from our development process. So it's easy to analyze by tools, but it should really start even with the requirements. We can do some kind of quality analysis, and the design or architecture of the system also should be analyzed regarding its qualities. So what are quality models? Quality models in a nutshell. Quality is defined as the totality of characteristics of an entity that bear on its ability to satisfy stated and implied needs. That's for sure a true definition by the ISO 8402, but it is also fairly abstract. Yeah? So the totality of all characteristics that are important for us, basically. Yeah? And that basically satisfy explicitly stated but also implied needs. And several years ago, the field of software quality modeling came up to break down that abstract term of software quality into more tangible concepts that are easier to touch and to deal with. And the software quality model basically supports an organization in systematically evaluating the quality of produced artifacts from their development process. So as you can see in the example on the right-hand side here, basically software quality is broken down from typically a quite abstract concept such as maintainability into more measurable concepts down to the level of concrete metrics that we can calculate and that we can hopefully subjectively measure based on one of the measurement objects. So your source code, the architecture, the requirements document, the test cases, and all the other things that could potentially come into play here. So software quality models specify quality characteristics of interest. They try to break it down, how to measure that. Also supports interpreting the measurement results. So we may have some kind of visualizations, as you see here. We already had in the last learning module this three-dimensional tree maps that are used for visualizing, for instance, the outcomes of a static code analysis, but you can use it in many different ways. But it's important somehow that we have, whether it's a bar chart, a more sophisticated visualization, we need some things that the practitioners can work with. And of course, it depends on the stakeholder that you have to deal with. If the viewpoint of measurement is the developer, a developer needs much more concrete outcomes. So the concrete places in the code, for instance, that have to be fixed. Whereas a high-level manager, quality manager of the organization just wants to get the big picture and overview and see probably the hotspots, the typical types of quality issues that arise and how this can be fixed in the future. And it's also important, the last bullet here that states that the measures that basically we derive from such a quality analysis is that we have to integrate that somehow in the development process. So typically in practice, companies define so-called quality gates. So basically points in time in the development process where at which the software or the different artifacts could also be, as I said, the requirements document or the architecture, the design have a certain predefined quality. And if they don't have that quality, they are rejected. That's the meaning of a gate. So they can only pass the gate if the quality is acceptable. Otherwise, the artifact needs to be or has to be reworked in order to pass that quality gate. So at the end, what do we want to obtain by these quality models? Well, it's very similar to analyzing the quality of cars. So that's an analogy here I picked some time ago from a German automotive magazine, the ADAC magazine. And basically, we want to do something similar as this comparison between two cars. So we have some attributes. For these attributes, we either can measure these attributes in a subjective way, so like the cost of a car. So we just look it up in the list and it has a certain cost. So we have some known facts about the car. We have some subjective ratings, like how comfortable, how luxury the interior of the car is, for instance, whether it feels spacey or not. So we also may have some subjective ratings in the game. And we have, that's also important, if you have many different measures, many different metrics, as we have seen in our static code analysis, it is somehow important to aggregate them. And aggregation is a very sensitive topic. You really have to be careful not comparing apples with oranges here. So, but in order to really not have to have a look to each single metric and to be easier able to see the key problems, aggregation is really an important thing. And then finally, we want to get a kind of overall evaluation in order to make things really comparable and easier to evaluate and assess. So what standards are there? Well, there are a couple of standards in this area. Some really take a very holistic approach to the topic of software quality. Some of them do only address a specific quality characteristic and try to analyze this or make recommendations how to analyze this specific aspect. One of the, I would say, the mother of all standards in this area is the SQUARE series of standards. So SQUARE is an abbreviation that stands for Software Quality and Requirements Evaluation. And it's basically defining different areas, so-called divisions. So in each division, you may have multiple reports as part of that standard. And then these reports basically define some general quality requirements that systems might have. We have the quality model division. That's the central division we will have a closer look on, that basically specifies what qualities or quality aspects do exist according to that standard. Then we also have one division dealing with how to measure these quality models. We have also one area here dealing with how to evaluate the quality of a software-based system. And in the center, the quality management division is basically how to manage, how to deal with quality in general. And in practice, basically, this division is most frequently cited and referred to. The reason for that is that the quality measurement division defines some metrics and measures that you could potentially collect, but in practice, as experience has taught us, it's very difficult to really implement the proposed metrics in practice. The reason for that is they are oftentimes quite abstract. Just define, I don't know, count the number of issue divided by the overall number, and then the larger this ratio is, the worse the quality is, something like that. So that's in general, of course, a true statement, or in general helps us somehow to capture the concepts. But for really coming up with concrete metrics for a concrete environment, this is typically too abstract. And we really planned or started using that quality measurement division in research and industry projects in the past. And that really was the conclusion. So it's normally hard to apply the metrics that are defined there as is. Nevertheless, they give you some idea, let's say, in which area you could define the specific metrics for your specific project. The quality evaluation division in general is also partially used in practice, specifically when it comes how to aggregate, how to analyze, and come up with an overall evaluation of your system. Sometimes you will also find references to the previous versions of that standard, which is the ISO 9126, which basically was only referring to software quality models, and the ISO 14598, which was only talking about the evaluation process. But for the sake of time, we will only dig deeper into the quality model division. What we find there is basically three different kinds of models, but two of them are very similar. They only distinguish between an internal and an external view, but all the quality aspects inside are exactly the same. So in that sense, we have a model for internal product quality, for external product quality, and for quality in use. If you remember our basic measurement learning module, then we had that little figure that said, okay, we have the internal quality, which has an impact on the external quality, which in turn has an impact on the quality in use. And if you remember correctly, we also had the process quality should have an impact on the internal quality. So internal qualities are qualities that are interesting to us from an internal development perspective. So for instance, maintainability from an internal point of view may be extremely important for us because we're changing the product very frequently. So we must have a good maintainability. From an external perspective, maybe reliability is much more important compared to maintainability, as the customer wants to have a very stable product. And regarding quality in use, we again may have different quality aspects that are interesting from a user's perspective. So internal is development perspective, external is the customer perspective, and quality in use is the actual user's perspective. And now we have different quality aspects defined here on the top levels, and we have some breakdown of that high-level concepts into smaller level bits and pieces on inside these boxes. So for instance, functional suitability, so how well the software basically suits the functional requirements, is broken down into functional completeness, functional correctness, and functional appropriateness. And for all these terms, you find definition specifications, what is meant by that. So let's dig through these aspects on the high level. We've already taken a little bit a deeper look into these two areas, reliability and maintainability, as part of the last learning module. So the reliability and maintainability of a source code at least was defined there. And regarding reliability, the ISO 25010 breaks down that concept into the maturity of the software. So how mature the software is, how the extent to which it is available, things like uptime of the software, whether for some, I don't know, some reliability reasons it has some issues from time to time and is not running. So that can be a metric in this area. Then how fault tolerant the software is. So if I especially use the software or give inputs to the software out of its original specification, whether it's tolerant to this or whether it crashes. And recoverability, once an issue happened and the software failed and was crashing, how quickly it can recover from that. Or in the area of maintainability, especially in our static source code analysis, of course, many different aspects regarding maintainability came up. Modularity, there we have the different coupling metrics that we talked about, and cohesion metrics. Reusability, that's another interesting aspect. So whether we are able to reuse parts of the software. Analyzability, it's important for understanding the software. So things like common density could play a role here. Modifiability, how easy or complicated it is to change the software. Things such as, again, coupling could play a role here, but also the algorithmic complexity, so McCabe's complexity could play a role here. And testability, of course, there also McCabe's complexity and other complexity measures could come into play to get a good coverage, for instance, of the different execution paths of a software. So at least on the high level, I want you to have a good understanding of what these so-called illities mean. So let's rush through. So here we have the quality aspects regarding internal and external quality. As I said on the last slide, functional suitability is defined as the degree to which a product or system provides functions that meet stated and implied needs when used under specified conditions. So that's it's suited according to the functional specification of the software. Performance efficiency means that the performance relative to the amount of resources used under stated condition, so that we have, according to the specification, of course, the system is performance efficient. Then the compatibility, the degree to which a product, system, or component can exchange information with other product, system, or components and or perform its required functions while sharing the same hardware and software environment. So this is basically how well it deals or coexists with other pieces of software. Usability, it's also nowadays more and more becoming important. Degree to which a product or system can be used by specified users to achieve specified goals with effectiveness, efficiency, and satisfaction in a specified context of use. And this is, you could also argue, okay, this should be a quality in use quality aspect, but here it's listed among internal and external qualities because it's very important to deal with that aspects early on. And a good usability then results in having, for instance, a performant or efficient usage of the software according to the definition of that ISO standard. Then the reliability, the degree to which the system, product, or component performs specified functions under specified conditions for a specified period of time, so that it's working according to specification. Security, degree to which a product or system protects information and data, so that persons or other products or systems have the degree of data access appropriate to their types and levels of authorization. Also, that aspect becomes extremely important with the IoT era, where all the also embedded devices become available in the virtual world, and some of them, as we can read in the news, have some issues in protecting information and data because it was not really required in the past because they were isolated from other systems and not available in the internet. Yeah, so this again, we come in this lecture always to the point where the environment or the context in which we are doing something plays an important role. So in a certain condition or usage context, some properties might be more important, and in another context they might be less important. That's the reason why we have to understand the environment or the context in which a software actually is used. And if we put it from or take it from that context and put it into a different one, we need to be very, very careful that the same quality aspects are relevant in this context as well. Maintainability, we already talked about that, degree of effectiveness and efficiency with which a product or system can be modified by the intended maintainers. That's important. So we are not talking about a completely different group that has never seen that software before. We're really talking about the people who intend to maintain the software. For them, it should be documented appropriately. From time to time at the Institute, the Fraunhofer Institute, we have projects which ask us to assess the software or evaluate a software regarding transferring it from one company to another company. So sometimes companies are buying external pieces of software or whole companies and trying to integrate that. And then it's also important, of course, that not only from an internal perspective, maintainability is there, but also from an external perspective, so that people who did not work with the software before can quickly get into maintaining the software. By the way, that also became more important in the area of outsourcing, where some development activities, especially coding, was outsourced to different countries. And of course, if you have frequently changing development teams that work on the software, good maintainability really becomes a key argument here. And finally, portability, the degree of effectiveness and efficiency with which a system, product, or component can be transferred from one hardware, software, or operation or usage environment to another one. Finally, here we have the quality aspects regarding quality in use. So first of all, the effectiveness, the accuracy and completeness with which users achieve specified goals. So this is basically how well or how good in terms of accuracy and completeness the users can achieve their goals with the software. Then the efficiency, it's how much resources are basically expended in relation to how good the software works. So it's accuracy and completeness with which users achieve goal or their goals. Then the satisfaction, the degree to which user needs are satisfied when a product or system is used in a specified context of use. So that's, of course, also depending on how you measure that, more subjective in that sense. Then the freedom from risk, the degree to which a product or system mitigates the potential risk to economic status human life, health, or the environment, so that it's freedom from risk. Then the context coverage, finally, the degree to which a product or system can be used with effectiveness, efficiency, freedom from risk, and satisfaction in both specified context of use and in contexts beyond those initially explicitly identified. So this is basically how well the usage context is covered, the intended usage context, and things that go beyond this extended usage context. So that was the quick overview of on the high level of this ELITs. As I said in the beginning, only a few of them we will go into more details. We already went into some more details regarding reliability and maintainability. So how are these quality models structured? So what conceptual elements do we find in there? And basically, as you have seen, based on the ISO 25010, we have an abstract concept that is broken down, refined into some sub-concepts. So such as maintainability is broken down into analyzability and modifiability. And we have some metrics which try to somehow quantify these sub-concepts. We may have, of course, a further refinement structure before we come to the metrics. So in this example, and also in the case of the ISO, we only have the high-level concept, like maintainability and the lower level concepts, but of course you may have a hierarchy of sub-concepts there. But finally, you will end up with a leaf concept for which you can assign some metrics. And we also want to know how to interpret the metrics values. So therefore, we may have evaluation criteria which say, okay, this is an acceptable threshold. So for instance, if our analyzability is measured by cyclomatic complexity, or one metric assigned to analyzability is cyclomatic complexity, then we can say, for instance, okay, the cyclomatic complexity for each function should be between 1 and 10. And then we also may have some aggregation method. So as you have seen in our analogy to comparing two cars with each other, we also want to have the ability to aggregate these lower level concepts. But how to aggregate something like a cyclomatic complexity and a coupling metric? Yeah? So therefore, we need to think about how to make them aggregatable. Oftentimes, we are using certain normalization functions for doing that. And similar as for GQM and GQM abstraction sheets, we may have additional variation factors which explain variations in our quality factors, so have an impact on the quality factors. So for instance, if you have experienced developers, this may have an impact on the maintainability of your software. Let's have an example. So let's assume we want to break down want to measure maintainability. We want to define a quality model for maintainability. So we break it down in this example into adaptability and analyzability. Then we think about how to measure these two concepts. So here we have two examples. So adaptability in this example is measured by cyclomatic complexity. You may have additional metrics, not only one. And commons density is a metric for the analyzability. We also remember GQM. We need to think about, okay, what is the measurement object? So which object do we want to calculate metrics for? In this case, the software code. So we want to measure the cyclomatic complexity, for instance, of all functions of our software code, and the commons density also of all classes or modules of our software code. And we have two impact factors here, variation factors, the time pressure, which is simply a subjective rating between high, medium, and low, and the developer experience here measured by the number of projects a developer has worked in a certain domain. So factors typically become more technical the more you break them down. So then it's getting more concrete towards also the different software artifacts or parts of these artifacts that we want to know something about from. So then let's think for a minute about how to aggregate these results and finally use the data for making some decisions. And let's use the analogy to a quite popular approach in decision making, which is the multi-criteria decision-making approach, the MCDM approach. And this example is about two cars again, and we want to select the best car. So that's our goal. We want to take the cheapest car with an acceptable capacity. That's the so-called preference relation. That's the one that we would like to select. And we want to select the best car based on some criteria. And so cost is one criterion here. And the capacity, which we say we want to have a car which has a capacity of more than 4 persons and a cargo load of more than 700 liters. And then we can define some sub-criteria. So the cost is broken down into the purchase price, the cost we have for fuel, and the maintenance cost of the car. And the capacity is broken down into the passenger capacity and the cargo capacity. So in that list, we have some items which are easy to aggregate, so which are comparable. So the purchase price, fuel cost, and maintenance cost are all measured using the same unit, namely, I don't know, a currency like euros or dollar. And then you can easily add them up. Maybe you have different weights. So how important is the purchase price compared to the fuel cost, compared to the maintenance cost? And we have several items that are non-comparable, such as the passenger capacity and the cargo capacity. So you cannot simply add up 4 persons and 700 liters. This does not make sense. So in that sense, we need to think about how to aggregate these numbers. Yeah, and these items are then easy to measure for all the alternatives or alternative cars in this example that could come into play here. And based on that, we have clearly defined criteria. So for instance, we will reject all cars that have a capacity of less or equal to 4 persons and a cargo load of less than or equal to 700 liters. And then based on the remaining cars, we can, for instance, use the cost for filtering them. So we take the cheapest cars that fulfills our capacity criteria. And then this basically can be used for decision making. So in this example now basically transferred to our area of software development. We want to evaluate or assess software. We have probably maintainability and reliability as two criteria that are non-comparable. So we need to think about how to aggregate them if we want to aggregate them. And we can further break down maintainability into degree of documentation, code complexity, naming convention, and reliability into defect density and coding restrictions, for instance. And based on these product factors, we can come up with some concrete data, so the measures at the end of our software product. Let us have a look to a more complex example here. And let's go back to our maintainability example. And we were measuring maintainability as cyclomatic complexity and Commons density. And let's assume we have some concrete data for some piece of code. And let's assume the average cyclomatic complexity across all functions is 6. And the Commons density is 2. Commons density here in the sense of that for each line of code, we find 2 commented lines of code. I know it depends on how you define Commons density. You can define a percentage value, or you can define how many commented lines of code you have on every uncommented or every source line of code. And now we need to think about, okay, how can we aggregate these numbers? And therefore, we define so-called utility functions. And we have 2 utility functions here. Let's start with the utility function on the left-hand side about cyclomatic complexity. And you see the utility function now maps this metric value to a scale from 0, which is in this example worst situation, to a 1, which is the best situation. And now, so on the y-axis, we find this transformed value based on the utility function. And on the x-axis, we have the cyclomatic complexity values. So if cyclomatic complexity is 0, we see that's in theory the best situation, will seldomly happen. And if cyclomatic complexity is equal or greater than 10, from there on we have worst evaluation, and we have defined an additional veto here where we would reject every software that has a cyclomatic complexity of greater than or equal to 20. Now, based on this linear evaluation function, we can get the value for cyclomatic complexity 6, which is then mapped to our utility function by our utility function to 0.4 on a scale from 0 to 1. So using the utility function, we basically harmonize the scale. So we map it to a kind of evaluation scale already. In this example, the evaluation scale is between 0 and 1, and then the values can be aggregated formally. If you look to the example on the right-hand side, the evaluation scale looks slightly different. So we have here Commons density. Commons density is here defined, as I said, the number of lines of code you have commented compared to the overall lines of code. And if you have not commented at all, it's the worst situation. Again, we have here the worst and the best situation. And if you have more than 3 lines of code per lines of code overall, that could be a little bit too much regarding comments. So then it also becomes the worst situation again. And then we have this triangular function. So the best case is 1-to-1, which means each line of code you have in addition 1 commented line of code. And then based on that, you can read out. So if you have a 2 here, it gets evaluated as a 0.5. And then on the top level, now we can aggregate these numbers 0.4 and 0.5 using these values. And then we come up with a quite abstract value of 0.444. And in order to make that, the interpretation of that value a little bit easier, we can map that in addition to an assessment scale. So here we were using some grades. So you get 6, the worst grade. So it's according to the German school system, the 6 is the worst grade. If the value is between 0 and 0.3, you get 5 between 0.3 and 0.5. And the best is achieved between 0.92 and 1. And with a 0.44, you see we get here a grade of 5. So this is one example how you can aggregate the raw data, the metrics data, to a kind of indicator. And of course, you have also an impact, time pressure and developer experience, as we had in the previous example. So normalization is performed by these utility functions in order to being able to really aggregate these numbers, and for being interpretable as an indicator, a mapping to an assessment or evaluation scale is performed. And if you remember our ISO 15939 from the measurement basics chapter, you see that the structure quite nicely fits. So on the low level, you have some base measures. Then you use this utility function to calculate two derived measures. And then you have an analysis model for calculating an indicator based on that. This is the quality model development process, so how you can construct basically your own quality model. And it starts with the characterization phase. So defining in which environment, in which context we want to use our quality model, depending on the context, depending on the scope of the model. So on which parts do we want to focus? We need different quality aspects that are important to us. So as soon as the environment and focus, the scope of the model is defined, we can define the quality modeling goals and then search for an appropriate existing quality model. So we do not have to start from scratch. We can start defining our quality model based on an existing model, such as the ISO 25010. And then from that, we can define, adapt, and tailor the quality model to our needs. So regarding the ISO 25010, as I have said earlier, we need to think about what metrics can we, for instance, use for measuring the different quality aspects that we want to consider. And then we need to define and set the baselines for our model. After the definition phase, we have to think about how to collect the data. So the measurement process basically is defined. We need to define a plan from which data sources we can collect the data, retrieve the data. We need to think about data collection mechanisms. So for instance, if we're using a static code analysis tool, we have to define whether this will manually be executed like you did it in the exercise sessions, or whether we will integrate that in the nightly build environment, for instance, so that we can analyze fresh data in the morning. We also need to think about, if we have different data, where to store the data. Maybe we will set up a data warehouse for storing the data, and we also need to think about who has to look at the data at which point of time and what kind of visualizations are required. And based on that plan, we start measuring the quality, we start collecting the data and using the data for assessing the quality of our products. Then we can analyze the data, validate whether our evaluation and assessment results are correct, and check our quality model whether it needs some improvement. And then finally, we can package the model, we can correct and adapt our quality model, and initiate also product improvement action. So based on the findings from the model, from the analysis step, we can identify the hotspots that need to be fixed, need to be addressed, and then we can initiate corresponding improvement actions. And that's basically the whole cycle for quality modeling. This cycle was not developed from scratch. It is based on a quite prominent improvement cycle that is used in combination oftentimes with the GKM paradigm, the quality, the goal question metric paradigm, And this cycle is called the QIP, the Quality Improvement Paradigm. So if you stumble across these 6 phases: characterize, set goals, choose, process, execute, analyze, and package. That's also the reason why they are called like that. That's basically the quality improvement paradigm. So let's have a look at an example. So in this example, that's based on a real case in the automotive area. And this was one manufacturer that we collaborated with some years ago. And the idea was to increase the software maintainability, so to check the maintainability of software components. And as I have said in the introduction, software is more and more used also in embedded devices, specifically in the automotive area. A car has different control units that communicate with each other. In a high-end car, we find more than 70 different control units. And in a lot of these control units, software is actually running. The software and the control units are normally not produced by the manufacturer of the car itself. It is provided by external suppliers. And sometimes that may also be the case that a control unit of a car will contain software of more than one supplier, so that you have a kind of larger processor, a larger, more powerful hardware, and on top of that hardware we will have software running from multiple suppliers. And of course, more complex functions require more interaction of different control units in a car, which increases the distribution of functionality across the different control units. So, for instance, you have the central control unit, an entertainment unit, you have an engine control unit, you have a lot of smaller units that control the window lifters, blinkers, lights, and air conditioning, and a lot more. And of course, in your head-up display, in your central unit, you want to see the status, for instance, of the different items that you have in the car, and therefore, of course, you need a certain communication effort. So the complexity of these control units is also continuously increasing, and the effort of putting them together is quite high, especially in testing the integrated functionality. So that's the general scope in which we work here. So the goal based on that scope is to reduce the maintenance cost of these control units, to ensure that we have a high quality of the software contained in that control units, in order to reduce the problems that we have during this effort-consuming integration testing, and afterwards the fixing of all the issues that we found during the integration. So that's more the motivation, the business level goal. On the software level, we want to therefore improve the maintainability of a single control unit. And the measurement goal, according to the GQM paradigm, is as follows. We want to analyze a single control unit software for the purpose of evaluating and assessing with respect to the maintainability from the point of view of a developer and an external supplier in the context of the car construction phase. So the next step, according to our quality improvement paradigm, the improvement cycle, you can see the cycle, a visualization of the cycle on the right hand side. So we are still in the we are now in the second step, setting goal and defining our quality model. As I said, we will not start from scratch. We will select an appropriate quality model from literature. That's a survey we conducted a couple of years ago. that found close to 80 quality models that we classified according to 15 different criteria. Some of the criteria were related to whether it's more a scientific model, whether it's a model that is applied in practice, or whether it's a national or international standard. We also distinguished between general purpose models who try to address quality as a whole, or specific models that have a specific quality aspect such as maintainability in their mind. And for our example, let's assume we analyzed the literature and checked what model is mostly appropriate for us, and the decision was made that we will build our own quality model based on the ISO 25000 the square standard. Let's build up our quality model, and based on that goals, we conducted workshops and interviews for building up our model. And final decisions were that we actually need two different quality models, one addressing the quality aspect of interest, namely maintainability, and to break this down to make this measurable. So these should contain things that we can directly, that we want to optimize, that we want to improve at the end. And another model documenting influencing factors, the variation factors in our GKM abstraction sheet. If you remember, we always have that two sections, one section trying to measure the quality focus of interest, and another section trying to capture the variation factors. So in our case, we decided together with the experts from the company to cut down maintainability into 4 sub-qualities, such as adaptability, for instance. So if you would map our quality model to the GKM paradigm, on this level, we have the top question that asks, okay, what is maintainability, or how can we characterize maintainability? Then on the next level, we can ask for how adaptable is the system, how analyzable is the system, and so on and so forth. And then we further broke this down to metric groups. Each quality aspect has a number of metric groups answering then GKM questions on the next level, like complexity related metrics, how complex is the system. And then finally, we have the metrics, and one metric is in this model exactly assigned to one such group. In practice, you also find models where one metric is part of different branches of our breakdown decomposition tree. Metric groups can also be assigned to more than one sub-quality. So the matrix is assigned, in our case, to one such group, but at least the groups can be assigned to more than one sub-quality. You will see that in the visualization in a second. So this is the overall model that we developed for maintainability. So here you see on the top, we have the main concept of maintainability. This is broken down into analyzability, adaptability, stability, and testability. And then for each of these sub-aspects, we have assigned different metric groups. For instance, this group is dealing with documentation, and we have different metrics assigned to that, like guidance per lines of code or commented lines of code. These are two metrics that assigned to that group. We also have, for instance, coupling related metrics like fan in and fan out metrics, coupling between objects, or some other things here that you already know regarding internal complexity. For instance, also cyclomatic complexity per function or the average lines of code per function. And these groups, as you see, can be assigned now to multiple quality sub-aspects. So, for instance, the internal complexity is part of analyzability as well as part of the testability of our product. So that's the basic structure, and you also see this light green numbers. These are weights. So basically it defines how important is one such subgroup of metrics for the factor. So in the case of analyzability, for instance, the factor internal complexity is twice as important as all the other factors. Or here on the top, the analyzability and the adaptability are 3 times as important as the other 2 factors, stability and testability. So this is the second model I was talking about regarding the influencing or variation factors of maintainability. Here we need to think about, okay, what has a positive or potentially negative impact on the maintainability? And here we basically have some metric groups that are regarding how the control unit software is embedded into the control unit itself, such as the physical partitioning. For instance, this is one factor regarding the analyzability and the logical partitioning. So this is basically says us something how the control unit itself is communicating with other control units. Typically in a car, this happens using a bus system. We have different types of bus systems, CAN bus or MOST bus, for instance. And via this bus system, we can send some messages. And via these messages, of course, one control unit is coupled with another control unit. And this is basically measured using the physical partitioning matrix and the logical partitioning matrix. So if certain messages are sent around, for instance, to another control unit, we have a certain fan in and fan out, or other numbers of functions that are required for the functionality of our control unit. In addition, we also have information about the load of the control unit and the criticality of the control unit. After we have defined the 2 quality models, one for maintainability and one for the impact on maintainability, we have to think about how to assess now quality and impact on this quality based on our 2 models. And as you have seen in the previous slides, each metric group and subquality has a certain weight that defines how important the respective element is. And we map each metric to an evaluation scale between 1 and 5. 1 means very bad and 5 means very good. And then based on that, we can calculate a weighted sum for the groups, subqualities, and finally for all qualities considered. And the top level grades make then statements about the respective measurement goal. So we have then calculated, we call that on the top level a maintainability index for all direct factors addressing this quality aspect, and an influencing factor index for all variation factors that we have in our second model. In the next phase of the QIP, we are walking now to the set process phase. So we think about how the measurement process will be conducted. So in our case, a questionnaire was created for getting manual measurement data from developers and external suppliers. So it was not everything was completely automated. And we had a static code analysis tool that we used, the QAC tool. So that's a tool measuring C code. and it comes, or you can buy it with the MISRA extension, so that basically gives us the code metrics that you have seen in the static code analysis learning module. And based on that, we implemented a small Java program at Fraunhofer for assessing interface data of the control unit within the network of control units in a car, and compute the relevant metrics. So there was a database in which the information about the control unit was stored. So regarding the functionality of the control unit, the functions implemented, the messages sent around, and you could export this data from the database, and we have written a small program analyzing this data. And then we put everything together in a big spreadsheet for comparing the different control unit software with each other. So the next phase would be the data collection phase, the execution phase of the measurement plan. And overall for this project, we analyzed and collected data for 10 different control units. All control units were implemented in the C programming language. But we had a problem with assessing the metrics, because if you only have 10 data points per metric, that's a little bit too few to really do some reliable statistics on top of them. And therefore, in order to be able to really compare two control units with each other, the relative distance for the metric values was computed and assessed on our evaluation scale. And we basically, as a workaround, we proceeded as follows. So if we have two metric values, A and B, of two different control units, and both are greater than 0, we define the relative distance as 100% minus the ratio between the minimum, the smallest value between A and B, and the largest value between A and B. And this basically defines how far apart the different values are when comparing two control units with each other. And we proceeded like this for all metrics in the quality aspect quality model, and for all metrics in the variation factor quality model. And the model indexes were then compared with developer statements regarding maintainability to check whether the model reflects also the subjective experience that the developers of these control unit softwares have at the manufacturers. So therefore you have to know that, as I said at the very beginning, the software itself is normally delivered by external suppliers, but on the manufacturer side, we have one developer who is assigned to that specific control unit and the software as well, and who has to work with that when it comes, for instance, to integrating the different control units with each other. So this person has a quite good understanding regarding the issues that arise from that integration. So these are the analysis results. We are walking further in the QIP to the analysis stage. On the right-hand side, you can see the maintainability index on the top levels. So regarding the 4 quality aspects of interest: analyzability, adaptability, stability, and testability, and the overall score for the maintainability. And on the lower right-hand side, you see the influencing factor index for all variation factors. Here you see two examples how we compared control units with each other. So here we have a control unit software B1 and a control unit software B2, and we basically have, as you see here, a very good evaluation for B1. So remember, the scale is between 1 and 5, and not so good value for B2 with 1.8. Remember, this was all calculated based on our relative distance matrix. But if you see here on the lower part, B1 had a quite negative impact from the variation factors, and B2 had a quite good positive impact from the variation factors. So how can we interpret these numbers? Well, in this situation, it's relatively clear because despite the fact that the environment, the influencing factors were relatively bad for B1, the maintainability was still quite good compared to B2. So in this case, we have a good indication that B1 is really quite good regarding the maintainability. So in our model evaluation, we compared the results of our quality model with the subjective assessment from the developers, and this really matched in 80% of all the comparisons. So we were quite positive about that the model really worked as expected. There was a significant difference in the size of the control units, size in terms of number of functions that were implemented. For those comparisons for which we did not have an agreement, a positive mapping with subjective evaluation from the developers. However, of course, we cannot make general statements about the models because we only have very few data points, but we had a quite good impression from the model application at that time. So let's continue with the last phase of the QIP, the packaging phase. So the analysis was then discussed in a workshop with our customer, and the feedback to the data collection resources was provided. So that's also an important thing to consider, that if people contribute to such a measurement program, they also should get feedback about what happens with the data, what was done with the data, what were the analysis results. And based on our analysis, some improvement actions have been defined. So one of them was to establish a reliable baseline really for comparing control unit software against this baseline that requires that we simply continue measuring and fill our database of control units so that we can really calculate some reliable thresholds for different types of control units, because as we have seen also in the quality model regarding the variation factors, the impact factors, it is important there also for not comparing apples with oranges. So if you have a multimedia system in the car, that is of course only very hard to compare with the engine control unit software. It's something completely different. And also we need to think about regarding which aspects we really want to compare which types of control units with each other. So to have meaningful clusters to compare control units. One further improvement action regarding the model was to reduce the effort collection overhead. If you remember, in this third phase, the measurement plan, we had some data that still had to be collected manually, which can be problematic or can be effort consuming and be an obstacle for deploying and rolling out such measurement models, and some further that I do not want to discuss here at that point in time. So this example hopefully gave you a good image of a real case in which we applied that QIP cycle and ran through that cycle one time. Towards the end of this learning module, I want to highlight one additional topic, which is technical debt. So the technical debt basically reflects implied cost that come from neglecting maintainability when developing software. So you have to imagine that when software is developed over years, or some software even over decades, new functionality is added, existing functionality is removed, and so on and so forth. And over time, we may have an issue regarding being able to quickly change and adapt the software. So this is a little bit illustrated on the right-hand side in this figure. So basically, this green curve represents the functionality that is added to the software. And at the beginning, of course, a lot of new functionality is added. But in a lot of cases, and we work together with companies where this really was a big issue, the focus was solely on functionality and not really on adding software that is easy to maintain in the future. And the reason for that is that writing code that is maintainable, or coming up with an architecture that is maintainable, is sometimes more effort consuming than just doing it a quick way. And of course, maybe the functionality that the end user sees, or that the customer sees and gets, is the same, but it's done in a quick and dirty way. And the problem with that is that later on, when you have to touch that specific functionality, it's getting more complicated in changing the functionality. So that is indicated by this red curve. And the red curve basically represents the technical debt that comes from that neglecting maintainability when developing software. So at the beginning, when focused on delivering new functionality, the technical debt is growing. And because of that growing technical debt, you will lose speed in adding new functionality. Up to a point where basically the whole development effort and team becomes less productive because of that technical debt in your software. So the goal is to really have at the end a balance between the functionality delivered and the quality delivered. Of course, there is always a trade-off between these two, but in practice, the challenge is to find the right balance there. And technical debt is a term which basically can be split down into two different concepts. On the one hand side, the principle that represents the cost of removing a quality issue. So basically trying to repair what was not developed in a maintainable way in the past. And the interest basically represents the additional work, the overhead that was caused by that quality maintainability deficit. And basically the technical debt is then the addition between these two concepts, the principle and the interest. So how to measure technical debt in practice? So this is an approach we developed in the context of a publicly funded project together with some industry partners. But the general approach is always quite similar. So first of all, you have to think about how to measure the root causes of technical debt, namely code smells or issues in quality issues, quality deficits. And for that purpose, we developed a quality model that contained the metrics that we see as relevant for technical debt. So maybe, I don't know, a very high coupling of components, low cohesion, high algorithmic complexity, large components or too large components or functions and things like that. So all of these things were contained in our quality model, and the majority of the aspects came out from a static code analysis. And then the critical point is how to map that to a cost figure so that overall you can calculate how many euros or dollars it will cost you to fix the system and maintain the system. So basically the critical task is to convert this code smells or the quality deficits into a cost figure. And the easy way is, like you have seen also in the SonarCube tool, is to assume that fixing a certain line of code will take a certain amount of time. So then you know how much effort is required for fixing all the quality deficits you have identified, and then to convert that to euros or dollars by using some hourly rates for developers. That's the easy way, but this may also be quite inaccurate because it depends on, of course, you can say, okay, for different kinds of deficits, I define different time spans. But the question is, does this really fit to the specific development context of your team? And the approach that we took here was to correlate the data with their defect tracking system. In the defect tracking systems, they had some information how long it took them for fixing certain kinds of issues, quality deficits. And from that, we tried to calculate the technical debt. So what you can do there then is, once you have identified this quality aspects that are important for technical debt, is to define some control limits, so upper and lower bounds. So from statistical process control, maybe you know this kind of approach, and then check whether your metric, like, I don't know, coupling or cohesion metric, stays within the defined threshold. And if not, we find some quality deficits that the development has to take care about. As mentioned at the very beginning, it is important to convince management that we have a quality problem, because otherwise management will always insist on creating functionality that the customer pays for instead of writing very maintainable software. And therefore, we try to convert that into that monetary value. And this monetary value is composed out of two components. One is this principal value, and one is the interest. And the principal value we can quite nicely get from analyzing our existing piece of software. We can say, okay, it has that many code smells, and whatever, whether you take the easy approach or the complex approach that we took, to convert that into an effort and a euro number. But the more difficult part is to do an estimate of the interest. So how will that slow us down in the future? And this is always a very complex or a difficult task to create that estimate based on your current productivity. How much will the productivity go down based on this technical debt principle? And for that, we again used our effort data from the defect tracking system to make some kind of estimate for that interest as well. And once management becomes an estimate that at point T3, I don't know, in 3 months, we will come into serious problem because we will be slowed that much down by our technical debt that we have to react now. And then management has some concrete argument based on numbers, based on a qualitative analysis that we have to react and probably come up with a development plan for improving the quality of your product, and can forward that plan to development to react accordingly. And of course, we also want to improve our model, so therefore we have an improvement cycle here based on the actions that were taken. We probably come up with that some kind of quality deficits still are missing in our quality model, and we have to add them appropriately. So that's the end of this learning module. As always, I would like to have a quick look to some measurement goals that are related to the things we have discussed. So basically, as we were talking about quality models, a quality model can help you to evaluate the quality of many different measurement objects. So whether it's we want to evaluate the functional suitability of the requirements from the point of view of a product owner, or whether we want to evaluate the maintainability of the software architecture from the point of view of an architect, or whether we want to, as we did in the previous learning module, evaluate the reliability and probably maintainability of the code from the point of view of a developer. So we may have many different aspects here that we can analyze using this software quality models. And of course, the question for you at the end, how would you measure these goals based on the models introduced? For some, I think we have already quite good examples in the lecture. Some others we did not really address, like requirements and software architecture, but you can think up based on the examples that we had how we could measure these objects as well. So conclusions. I hope you've seen measuring software quality is a central dimension of measurement. It's a key application field of measurement. The quality models help us to really break it down to something that is measurable. So they help in identifying, first of all, what quality are we interested in. There are many different aspects, and we need to focus on some of them. It's not a good idea to say, okay, quality is everything for us, and let's try to have the perfect quality and measure that across all the quality aspects defined in the ISO 25000. You can do that, but it's probably a little bit too much. So you always have to find the right balance between quality on the one hand side and functionality on the other hand side, and what qualities are relevant for your specific context. And therefore, we're using quality models. We've also seen that if we want to get a kind of assessment or evaluation of the overall quality or some quality aspect, we have to make metrics comparable. Normalization is one way to make them comparable so that we can really, for instance, normalize the metrics, map the metrics to an evaluation scale, and then having a unique scale that we can use for aggregation. The more abstract the metric, the more difficult to interpret the numbers that we have seen. At some point, we have to remember these utility functions. This is the critical point to map that to an evaluation scale. There we have to decide what are good and what are bad numbers at the end. So how to really interpret the derived metrics so that we can come up with an easy way, or as easy as possible way, to interpret the numbers. Building up meaningful quality model requires historical data for determining meaningful evaluation criteria. You have seen that in our automotive example, where we did not have sufficient data. We can tweak a little bit around and do pair-by-pair comparisons and do a little bit of calculation there. But at the end, you really have to establish a kind of historical database for doing some statistics and then analyze what are meaningful thresholds. That's the one way to analyze your own data. The other way would be to rely on a standard that probably defines some thresholds. In some cases, we find that. Remember also the last learning module about static code analysis, where we had this HIS initiative and the metric thresholds defined by the HIS and MISRA initiative. And finally, we also had a quick look to technical depth. That is one important application field of quality models. So you basically have to have a certain quality model in the background for calculating technical depth properly. That's it for this learning module. As always, you also find literature recommendations on the right-hand side in case you want to take a deeper look. I also can especially recommend the final paper from one large research project that we had on quality modeling, the Quamoco project, that is also available online. And I highly recommend that if you want to take a deeper look on the structure of these quality models. So thanks, and hope you also join the next learning module of the lecture. Goodbye.